Thanks. I'm going to present joint work with Dohan Kim, Teppei Saito, and Akihisa Yamada. And in this talk, I will first give you an introduction to what I'm actually doing. So I'm working on certification of non-reachability in term rewriting, and I will explain all of these three words here, certification, non-reachability, and term rewriting, one after the others. So certification for me means not verifying a program, but checking that the output of untrusted tools is indeed correct. So I'm considering some unverified tools as they are participating, for instance, in the termination competition or in the confluence competition, which are given some validation task, and then they produce an answer. For instance, a given program is terminating or not, in combination with some certificate why this should be the case. And what we do is actually we try now to run this proof, which will generate this answer on the certificate, and all the reasoning that is done in the tool will be verified, formalized in some proof assistant, leading to some formalization, and this formalization is also equipped with verified algorithms to check whether these proof techniques are applied correctly. And then via code generation, we actually get a verified certifier, which can check then whether the generated answers of these automated tools is correct or not. And so we can then accept or reject such a proof. In our setting, the proof assistance we are using is Isabelle HOL, and the library in which we do our formalization is the ISA4 library, the Isabelle Formalization of rewriting, which at the moment mostly is about rewriting, but it also contains certain other languages. For instance, we also have a little bit of SMT solving and LLVM formalized there. So this is the framework of what we want to do. Now, what is our aim? The aim is what we generate here is the certifier that is called CeTA, and we would like to support more proofs that these tools are using. So in particular, we want to be able to certify more non-reachability proofs. And what this is actually an analysis that shows that something cannot be reached in the setting like safety proving, that starting from some initial state, we cannot reach a bad state where some property might be violated. Or in the context of a compiler, certifying that a certain code fragment cannot be reached, so we don't need to generate. Okay? Or in termination analysis, this is used to actually generate a tight approximation of the call graph so that certain parts of the code don't have to be investigated for termination proving. And non-reachability, proving these non-reachability is actually part of COCO. COCO is the international confluence competition, where one category in this competition is to prove non-reachability or reachability, which is also known under the name infeasibility, automatically on a set of systems. Now, this non-reachability we consider now here is in the context of term rewriting. What is term rewriting? Basically, it's a very simple model of computation where you just have, in our setting, first-order terms on the left, which rewrite to first-order terms on the right, where here, for instance, we see the three rules implementing the Ackermann function, and here we have rules which check whether a given argument is a natural number or not, where the natural numbers here are using piano notation, so zero and successor notation. And here in this talk, I will restrict to plain first-order rewrite systems. In the paper, you also find results about conditional rewrite systems, which is an extension of this formalism where you can have side conditions on the rules. Good. What is now the question of reachability? The reachability basically takes two terms, a source term and a target term, S and T, And then the question is, can we instantiate the variables in the source term and in the target term in a way that I can rewrite from the starting term to the target term in arbitrary many steps? This is an undecidable problem, and example problems might be, for instance, is it possible that from Ackermann 7,7, and then I want to check whether this is a natural number, that I can rewrite to false? In this way, this example is a very trivial one in the sense that here there are no variables occurring. So trivial task, I just have to rewrite to normal form and check what is the result. Although you don't want to rewrite Ackermann 7,7 to normal form. That would last a little bit too long. So then we can replace certain subparts by variables. For instance, instead of here having a 7, we can just write a variable here, and then the question is how to instantiate this. And the answer is again no, but now it's a little bit harder to see that this is non-reachable. Or we can even substitute both arguments of the Ackermann function by variables. And now, however, the answer is yes, because you can plug in for x the value 0, and for y you plug in true. And then by the first Ackermann rule, you rewrite the inner arguments to s of true. And then via the is-not functions, you end up in is-not of true, which yields false. Okay, so it's not always obvious whether some reachability problem is satisfied or not. Now, non-reachability in terminal writing is, as I said, a subcategory of the confluence competition, and there are various tools that try to automate these proving techniques. And for instance, the two tools, NUT and InfChecker, they actually can synthesize non-reachability proofs for the first two examples that I've shown you. And the tools InfChecker and non-reach, they actually can automatically find a reachability proof of the third example. The problem is that all of these proofs that we have here of these tools cannot be certified because the power of our certifier CeTA is actually limited at the moment before this work to syntactic algorithms to check non-reachability, or to use tree automata approximations, where the tree automata is used to over-approximate the set of reachable terms and then show that this is disjoint from the target terms. Or it can also take detailed rewrite sequences for reachability. In principle, the tool here of non-reach would be trivial to certify. Unfortunately, here the non-reach tool does not output any machine-readable proof at the moment. So what we want to do now is we want to extend the formalization and the CeTA certifier in a way to support non-reachability, not via tree automata or syntactic methods, but using term orders, in particular so-called co-rewrite pairs. And here there is a nice theorem of Akihisa Yamada, who showed that a given non-reachability problem is non-reachable if there is a co-rewrite pair, so a pair of relation being a strict and a non-strict one, such that on the one hand side, we have a weak decrease from all left-hand sides to the right-hand sides, meaning that this reduction sequence will turn into a greater equal, so by demanding closure under substitution and closure under context. But on the same hand, the target term is strictly larger than the source term. And putting these together, we would somehow have that S sigma is greater equal T sigma is strictly greater than S sigma, so S sigma is greater than S sigma. And assuming irreflexivity of the order, this is a contradiction. Okay, so this is basically what the properties of a co-rewrite pair are: irreflexivity, closure under substitution, and closure of context of the weak relation. And Yamada showed not only that this is a sufficient criterion, but this is actually an if and only if. So in principle, quite a powerful method, but of course it depends on which kind, how do you synthesize these co-rewrite pairs. So what is the easy part? We started by formalizing basically this theorem where we used the existing infrastructure of the ISA4 formalization that for many years supported termination proofs. And in termination proving, there is the notion of a reduction pair, where a reduction pair is basically a more restrictive variant of a co-rewrite pair. Every reduction pair is also a co-rewrite pair. So all the reduction pairs that are available in ISA4, like polynomial interpretations, matrix interpretations, path orders such as the lexicographic path order, Knuth-Bendix order, etc., the weighted path order, they can immediately be used to prove non-reachability by this result. So this was somehow a very nice start once formalized this theorem, and then just use all these available orderings, and we can have many more non-reachability proofs. For instance, here is now a certifiable proof which proves that this is non-reachable. We just here plug in a polynomial interpretation over the natural numbers with these interpretations, and then by calculating you can check that indeed all the left-hand sides are larger than the corresponding right-hand sides, and that the target term here is strictly larger than the source term. Okay, for instance, here we see that false maps to 2, whereas is not is just the argument plus 1, so we get 1 plus this result. The Ackermann interpretation is the second argument, so we need to compute the interpretation of the 7, and since successor is just the projection to the argument and 0 is interpreted by 0, this will be the 0, so the right-hand side is the number 1 at this point. Right, so this is what we immediately get now, and how does this look like now in the certificate itself? That is actually an XML representation of such a proof, where I'm just quickly going over it. So it's quite natural, it's not easy, not hard to generate. Basically here you see each rule is spelled out in XML, and there are 7 of them. Then you have the corresponding source and target term, and then you have the infeasibility proof where you give the interpretation of all of the polynomials for the various function symbols. And this is then passed the internal structure and then later on certified that indeed this interpretation satisfies all the required properties. Now, let's go for the harder part. The harder part is we really want to have the full power of the co-rewrite pairs. And the full power of the co-rewrite pairs means we want to drop the corresponding assumption of reduction pairs that we have strong normalization of the strict order. That is somehow the key difference between the co-rewrite pair and the reduction pair. However, since the whole development of the ISA4 library was tuned towards termination proving, in all of these term orders, strong normalization was used as a standard assumption on all the orderings that were implemented there. So just the interface to communicate with the orders did not allow to specify any not strongly normalizing order at this point. And to this end, we actually had to refactor and redesign our interface for the term relations so that now you can query these orderings after one property after the other, whether the order is stable, whether it's closed under context, whether it's transitive, whether it's reflexive. So you can query all these properties one by one. And then we additionally add certain convenience functions which bundle up certain properties to say, well, is it a co-rewrite pair or is it a reduction pair? In Isabelle, this looks like this. We have a big record type, rel impl for relation, term relation implementation, where basically we have here three relations, a strict one, a non-strict one, and another one, which are of a type, they take a rule, so a pair of terms, and give you back a corresponding Boolean result with an error message in case the constraint is not satisfied. Moreover, besides these relations itself, you can now query like flags like, is this strict ordering strongly normalizing? Is this strict ordering closed under substitution? And the ... means many more properties you can query. In a total, I think there are 23 entries in this record data type. Now what we have is, additionally to this record, we have a corresponding predicate that tells us whether this is a valid implementation, and that basically checks that what we have executable code, meaning, for instance, for polynomial interpretations, they are in general undecidable if you think of nonlinear polynomials, whether one polynomial is always greater than another one. So what we have here is implementation of sufficient criteria, executable sufficient criteria, which can ensure that a given term pair really is in the relation. And so we have things like that we have an under approximation of the actual relation, meaning that the thing that is in the corresponding record here, if that says it's okay, S and T are in relation, then indeed S and T are in the semantically defined polynomial order. And so what we have overall is we have approximations here. We have also approximations of the property. If the flag for strong normalization says it's okay, it is strongly normalizing, then you can be sure the real ordering, the semantic one, is really strongly normalizing. And on the outside, we know that if the global validity flag says I'm okay, then there are semantic versions of the relations which have the connection to the implementation version. And this validity flag might check something that actually the polynomials that you define really are polynomials over the natural numbers. If you would assign x minus 1 to something, then this validity check would claim that this is not allowed. So this was a major refactoring, and now we had to actually adjust all the term orders that are inside ISA4 to this new interface. And there, in particular, we run into problems on those parts which are transforming given orders to new orders. So, for instance, what we had before is a theorem like given a transformation like an argument filter, if we get as input a reduction pair, then the filtered orders also form a reduction pair. So if you have all the properties before, you get back all the properties afterwards. But now we had to do it much more fine-grained in the way that we had to check, well, to transfer closure under substitution for the filtered thing, you need closure under substitution, reflexivity, and transitivity before, right? And similarly, reflexivity carries over, and we had to do a much more fine-grained analysis on all of these properties. The final thing, what we actually did is, of course, now that we have the interface that supports co-rewrite pairs, we actually want to add further co-rewrite pairs which were not available before. And here, as a case study, we took 3 different co-rewrite pairs, namely polynomial interpretations where the domain of the polynomials are the non-positive integers. Where of course, this is not strongly normalizing because you can go down from -5, -6, -7, and so on. So it's not strongly normalizing, but it's still irreflexive. So it's a valid co-rewrite pair, and Yamada's work showed that for certain non-reachability proofs, reduction pairs cannot prove non-reachability, and polynomial interpretations over the non-positive integers can do it. Similarly, there is the weighted path order, which is a transformational method, and also the covariant. There is a co-WPO, which only works for co-rewrite pairs. So what we did for the polynomials, we tried to reuse the results that we had for the polynomials over the natural numbers. And what we mostly did is interpreting polynomials over the non-positive integers can be mapped onto polynomials over the naturals just by flipping all the coefficients and negating them, and then adding an outermost negation. And therefore, we can reuse all the algorithms that, for instance, ensure monotonicity or weak monotonicity of a polynomial, which we had for the natural polynomials over the natural numbers before. So there, this part could nicely be reused. For WPO and co-WPO, we mainly had problems because our original proofs sometimes used strong normalization in parts of the proofs. For instance, to show that if a property would be violated, then there would be a minimal counterexample with respect to the strongly normalizing base order, and these proofs just no longer work, since now we had to drop the assumption on strong normalization. Moreover, we detected in this formalization that extension of co-rewrite of the WPO by switching from lexicographic comparisons of the arguments to multiset comparisons. This works for WPO as a reduction pair, but for co-rewrite pairs, it does no longer work out, and there is a counterexample which shows that this extension is unfortunately unsound here. In addition to the formalization, we also wrote a small prototype tool which now really produces certifiable proofs for non-reachability proofs via co-rewrite pairs, where we implemented 3 different strategies: either use polynomial interpretations over the natural numbers, over the non-positive numbers, or use the WPO configuration. In comparison, we also looked at the certifiable version of non-reach and Mocha, which are tools which were run in the recent conference competitions on non-reachability. And the results are, well, not that impressive here, because with our technique, we are clearly weaker than the existing tools. However, we are complementary to them in the sense that from these small sets of examples, we at least got 8 new problems which could not be solved by non-reach and Mocha. And of course, by adding some of the syntactic approaches and the tree automata approaches that are built into the Mocha and the non-reach tool, the combined solver could improve quite a bit here. To summarize, what we did is an Isabelle formalization of co-rewrite pairs in order to certify non-reachability proofs. This involved a refactoring of the whole term relation interface. Theoretically, we figured out that co-WPO is unsound if one replaces lexicographic comparison of arguments by a multiset comparison of arguments. And experimentally, we at least figured out that so 8 new examples could be proven via term orderings. If you look into the paper, you also find proofs to show unreachability in the conditional setting, and I'm happy now to take questions.
Time for questions.
So your certifier CeTA is able to check these proofs that come out, and does that mean that you're also using it in these competitions to check if the certifying rewriters actually produce a valid certificate?
Yes, yes. So CeTA is used in the Confluence competition from the beginning to check the output of the proofs, and in the competition there are always 2 modes. There is the full mode where the tools may output whatever they want, and there is the certified track where indeed certifiable proofs have to be generated. And there are currently 2 different certifiers that are participating in the competition that can check parts of these proofs. So,
I see, and all of the sort of formats that these tools can output, or modes of proof, shall we say, can now be verified by CeTA.
Well, there are certain parts that cannot be checked. So usually it works like this, that in the certified track of the competition, the tools have to restrict to those techniques that are known to be certifiable by at least one of the certifiers. Okay, so they might have to turn out their novel technique that just had been presented somewhere, because that will not be able to be certified. So there will always be a small gap between what is certifiable and what the tools can actually do. And well, it's my job, or I try to keep up with the tools, what kind of proofs they produce. And if I see that a certain powerful technique pops up, then I might consider this worthwhile and investigate into formalizing it and integrating it.
Any other questions? I have one. I have a question about the example of Akama function. Is that problem is it possible to solve that problem by using other methods? For example, reachability analysis by using tree automata approximation?
At least what I saw here, I mean, I don't know. I mean, tree automata, they might also be large, and they are computationally complex. I know that here the NUT tool was actually the first who implemented co-rewrite pairs. The NUT tool solves it also with an interpretation as I've shown you. But NUT, unfortunately, does not produce certificates in the machine-readable format. And the InfChecker tool, that actually uses a different approach by translating it into some first-order model, into some formula, and that is something which we definitely cannot check at the moment, but whether it is possible to use a tree automata encoding for this particular example, I don't know. The one tool, non-reach at least, that sometimes generates tree automata, that fails on this example.
Okay, thank you. Any other question?
This is maybe a bit of a wild idea, but is there any possibility of, shall we say, closing the loop where Isabelle, right, could maybe, where you may have a property, a reachability or non-reachability property that you want to prove, and then you could have a tactic within Isabelle that calls one of these one of these tools that outputs a proof that you then translate back into a proof within Isabelle?
Okay. Well, for this application, I don't know actually at the moment. What we did is, at one point, we translated termination obligations of Isabelle-defined functions into term right systems, and then actually re-imported this into Isabelle itself via our certifier to check that the corresponding first-order term right system really is terminating. And then we had a tactic which says that if the extracted term right system terminates, then also the function is terminating that you just defined in Isabelle. So in principle, that's workable, but in practice, it was not that useful, because for loading all of our theories, it takes roughly, I think, 3/4 of an hour to just compile all the theories at the moment. And you need quite some memory just to have this functionality, and therefore it didn't pay off in retrospect. So it is possible, but with limits.
Okay, let's speak again.